Hello, everyone, and welcome to 5 Ways Facebook's Ludicrous Usage Drives Presto Innovation. I am Ariel Weisberg. I am a software engineer at Facebook working on the Presto team. Some of these slides are relatively detail heavy, with the idea being you can look at them offline. So don't feel bad if I move past before you've had a chance to read them. There are also links to additional presentations that contain more detail on each topic. Presto is one of the two big compute engines at Facebook, the other being Spark. Presto is our more general SQL compute engine. We only use HiveQL with Spark, so there doesn't happen to be an overlap there. There are other things that use SQL, but they are generally specialized in some way. Presto is open source, Apache 2.0 licensed, and owned by the Linux Foundation. It features pluggable connectors that allow you to query your data where it already resides, whether that is HDFS, S3, MySQL, Postgres, Accumulo, Elasticsearch, etc. There's a long list. Some of these connectors are not that complicated to build. Presto provides consistent ANSI SQL interfaces over these connectors, so you can join data between systems and even union certain systems together to appear like a single data source. Presto is horizontally and vertically scalable, allowing each part of a query to execute across many cores on a single node, while also scaling out execution across multiple nodes at the same time. Presto is primarily used internally at Facebook. While data processed by Presto might end up in some other system that is externally visible, Presto itself is generally not used for that purpose, being a more flexible, open-ended analytics system. We have a pretty diverse workload. My guess is that outside of compute as a service providers and Google, you are unlikely to find more concurrent users, query authors, or unique queries all pointed at the same deployment. This contributes fundamentally to what drives us, as we are both developing and consuming Presto directly at a scale large enough to justify significant investment. I would love to have more detailed numbers for you. Unfortunately, patent trolls ruin everything, and I wasn't able to get approval for any specific numbers, but a large number of people will have a query issued on their behalf by Presto. This is going to be quite a large number due to dashboards and similar tools with wide audiences. The pool of query authors is significantly smaller, maybe 10 times smaller. And in terms of number of unique queries, it's a much larger number, a multiple of the number of unique query authors. And it's sizable enough that it really does drive our decision-making process, as we can't really afford to break these queries or significantly regress a large percentage of them. We divide up our workloads a couple of different ways. What we call batch is basically scheduled and repeating workloads that have to complete every day. Many of these queries depend on the results of other queries, both inside Presto and in other systems. And we have to land all of them and their dependencies in order every day. There are a large number of these, and breaking queries or regressing efficiency by a few percent can have serious consequences. The actual performance or reliability on any given day of a specific query is relatively unimportant, as there are automated retries and no one is waiting on the result. Slight differences in landing time, which is the time of day a query finishes, isn't that important for most queries. However, there are some that are considered high priority that do have stricter expectations that we deal with via tuning queuing behavior. The batch workload is the biggest workload in terms of capacity footprint. So if you want to save on hardware, this is the place to do it. We also have what we call ad hoc or interactive, which are queries that are sometimes repeating but not scheduled. This workload has very high expectations around reliability and queuing time. Queries should start execution immediately and not queue, because the expectation is there is a human waiting on the result. If more than 1% of users see an error in a day, it's considered a violation of our SLO. There is a similar SLO for queuing, but it's a little harder to describe. Workload growth is a constant fact of life. People want to do more and optimize less, and our data volumes grow even if no one does anything. Efficiency wins allow people to do more with Presto and reduce or even eliminate the capacity growth required. Many of these efficiency improvements can manifest as ease of use improvements and wall time, which is time to query completion improvements, that are beneficial even outside of Facebook. Memory is at a premium. Presto was originally designed to operate in memory and did not leverage disk at all. The workload grew to fit the amount of available memory we had, including the scheduled and repeating workload, which we can't break. And it's too large to just rewrite or optimize any of the queries that might be impacted. A small percentage of hundreds of thousands of unique queries ends up being a big number. At the same time this was happening, the economics of hardware changed, and the ratio of CPU to memory, we are expected to work with tilted heavily in favor of CPU and away from memory. The amount of memory available at each node was cut down to 1/4 of what we had. For an in-memory system, this presented some serious challenges we had to overcome, which I will discuss more later. The first thing I'd like to introduce is Raptor X. Raptor X is our name for an effort to implement several different forms of caching to enable Presto to run non-trivial queries sub-second. Our initial solution for faster, lower latency queries on Presto was called Raptor, and it relied on local storage with Flash. This was problematic because it created resource fragmentation and other complexity. By adding caching, we were able to switch to disaggregated Flash, resolving additional bottlenecks around schema, data, and metadata on data. Much of the data we fetch is just to find out what we need to know before actually processing any rows. Everywhere you see an orange line in this diagram is a place where we added caching to Presto to create Raptor X. It's still a normal Presto deployment on Metastore/HDFS, unlike Raptor, which requires and manages local storage. Raptor X adds caching for metadata, such as the statistics necessary to plan a query, lists of files, and the metadata to access files, metadata for stripes, which are independently compressed sections of files that can potentially be skipped. There is also a cache of materialized results of execution. It's not a query result cache, it's a fragment cache. This allows us to avoid recomputing the same data for each query, even if the queries aren't identical. There were a lot of challenges to solve around creating locality so that cache could work, and building cache keys so that queries that are similar but not exactly the same can still benefit from already cached data. You can see that in general, it's quite beneficial for TPCH. We weren't building Raptor X for TPCH in particular, so your results will vary depending on workload. Some of the workloads we were targeting did do better than 10x. Raptor X isn't magic and requires that your workload has some cacheable access pattern. Raptor X reduced the number of compute engines or database-like tools we have to support inside Facebook. This reduces redundancy in terms of the software we have to develop and maintain, and allows us to focus on making one system better instead of n different systems. This is a theme that's going to repeat. It also means we are sticking with a single fully supported SQL dialect instead of n different systems with different dialects, with some compatibility, but not really guaranteed. This is another theme that will repeat. Operationally, with disaggregated storage, we can now scale storage and compute independently for all these use cases. Previously with Raptor, we were storage bound and had a lot of idle compute. We can also focus on how to release and deploy Presto reliably and effectively, instead of having to duplicate that overhead for n different systems. James Sun did a full presentation on Raptor X at PrestoCon if you are interested in seeing more. This is the part that is near and dear to my heart, since I am the tech lead for the batch pod, and this is one of our focuses. I mentioned the batch workload, which is the scheduled and repeating workload. We further subdivided into small batch and large batch, and this is just an arbitrary division that we use for conversation purposes. Small batch is the workload that works well on Presto Classic, which is Presto with streaming execution, which most of you are already familiar with. Large batch is generally anything that is causing problems on Presto Classic. Long-running queries have poor reliability on Presto because if a single node fails during the query is killed and has to be retried. Queries are limited to the memory available in a single cluster, so we can only run a few memory-intensive queries at a time and the rest have to queue. If a query has skewed memory usage, we may not even be able to run it at all, and queries may start failing randomly after working fine for years just because they hit a memory limit due to organic growth. This creates a constant maintenance burden. Working around these limits via query optimization and rewrites creates a poor user experience. It's something people can live with when it's just a few queries needing optimization periodically, but it's a big problem if we need to make a change like moving to hardware with 1/4 of the memory. We can't derail entire roadmaps and orgs so they can go rewrite queries. We have 3 solutions. I am mostly going to cover Presto and Spark in depth, as it is the best option for most use cases and where most of the active development and focus currently is. Presto and Spark essentially runs Presto inside of Spark as a library, ensuring 100% SQL compatibility and similar performance with all the benefits that come with executing a query on Spark as an RDD. This is very similar to what Google did with F1 Batch initially. Presto Unlimited brings MapReduce style shuffle, which is the exchange of data between stages of query execution, to Presto, which allows you to partition the data over more buckets than you have nodes. This eases memory requirements, but doesn't help with skewed memory usage. That is what operator spilling is for. And it also doesn't introduce the full fault tolerance that we get from Spark. Operator spilling allows execution on any node to leverage local or remote disk to extend memory for query execution. Operator spilling is the thing you always need no matter what execution model you choose. And this is the classic runtime adaptive approach to papering over not having enough memory, or not having a good enough or adaptive enough execution plan for a query. Presto Classic's architecture streams data between nodes directly and everything is stored in memory. This allows Presto to start returning results for a query before query execution completes, hence the name Presto. Because of the streaming execution model, we can start returning rows at the root of the plan graph instead of having to wait for multiple exchanges to complete or multiple stages of execution to complete, as is required by Spark and Presto Unlimited. Presto is also a multi-tenant service with multi-tenancy provided by a single shared multi-threaded process at each node. This means there's no warm-up or startup delay, but also limited isolation between queries. It's very good at what it was originally created to do, but has no fault tolerance and does not scale to a large number of nodes. Presto Unlimited produces query plans that are identical to Presto Classic, but at execution time, instead of using in-memory streaming shuffle, a disk-based shuffle is used, with the data partitioned over n different buckets, where n can be any power of 2 that is less than 16K. This is mostly arbitrary limitation around number of open files and the memory required to open them and encode the file format. Each bucket can be processed independently, so not all buckets have to be loaded into memory at the same time. By avoiding loading everything into memory at the same time, the memory required to complete a query is reduced. Presto on Spark uses Spark's RDD API to describe the logical Presto plan to Spark and then embeds Presto as a library to run each node in the plan. Spark provides scheduling for Presto's evaluation on its own pool of hardware and handles fault tolerance. It also takes care of shuffling between stages, so exchange. And it uses the model that is similar to Presto Unlimited, but more robust, as you can plug in a shuffle service or use Spark's native shuffle and not have a limitation on how many buckets you partition your data over. Conceptually, Presto on Spark is pretty simple, and it was relatively fast to get to the point where all Presto query shapes were supported. It was the remaining 20% that took 80% of the time, dealing with things like shuffle throughput, broadcast memory variable efficiency, and memory efficiency and accounting improvements necessary to fit in the smaller container sizes favored by our Spark deployment. Presto on Spark is pretty much a full replacement for Presto Unlimited. There is a slice of short-running queries that require the memory reduction of Presto Unlimited, and this is where fast startup time is beneficial. It's likely we will continue using Presto Unlimited for short-running queries as the overhead of maintaining it seems to be low. Presto on Spark, especially with operator spilling, fixes so many things. Queries scale to large data volumes, runtimes, and skew instead of failing. Because we can share hardware between Presto and Spark can use a lot more hardware per query. So you can actually get faster well times despite not running all stages of a query concurrently because you're no longer using streaming shuffle. Isolation between queries drastically limits the blast radius of a bad or misexecuted query. Fault tolerance means infrastructure issues are far less likely to cause wasted CPU or delayed landing times for long-running queries. Fine-grained resource allocation and scheduling mean we don't have to fight with how many queries are running concurrently and whether they are going to compete and run out of memory. One cluster per region simplifies deployment and gives us less to manage and monitor. Fault tolerance also makes supporting elastic capacity, which is capacity that we can borrow from various pools, which may disappear at any time with relatively short notice, possible with good user experience and minimal wasted CPU. Query execution can go beyond or below 600 nodes and can vary during the lifetime of a query based on priority. Preemption is supported, so it's possible to optimize for queue time for high priority queries with less wasted CPU or unduly delayed low priority queries. The next thing to talk about is still very early days. So early that it was mentioned at PrestoCon, not even by name. So this is exciting. I'd like to introduce Velox. Velox is a clean sheet approach to a SQL execution engine. Velox is an execution engine, so it doesn't include a parser, planner, or optimizer. It takes as input a description of the plan you want to execute, and then the data you want to process, and outputs the result of executing the plan. In actual practice, you don't actually provide the data directly. It's capable of going and reading out of whatever data stores you have available, rather than having to re-implement that portion of the work yourself. Velox is not intended to be Presto specific, although being able to support Presto SQL is one of the initial goals. By factoring out an execution engine and embedding it everywhere, we can consolidate our efforts in terms of improving performance and capability across systems. It also makes it easier to provide consistent language features across systems, as there is less that needs to be implemented. There's a separate effort to unify the front-end parser and planner, but that is at an even earlier stage than Velox. Velox is currently in development internally. It's not publicly available, and I do not have a schedule on when or if that's going to happen. Unfortunately, I also don't have metrics to share. Velox exists and supports some query shapes, but it would be premature to share performance numbers at this point. The benefit of having eval and eventually SQL compatibility across systems is hard to measure, but it means your UDFs work everywhere. You can cut and paste snippets of SQL, and you have fewer things to learn when getting started with a new system. Some of the improvements we are looking at stem from better C++ code gen, mechanical sympathy from C++ idioms, better memory management, which is pretty much a requirement in C++, which allows us to more efficiently utilize memory, which is important when deploying in low memory environments. There's also just the benefit of having a complete rewrite with better implementations for the different operators. For specific benchmarks, some of these different algorithms and implementation improvements can really be substantial. I think outside of Facebook, there are fewer people who are interested in just efficiency, but many would appreciate a reduction in wall time. It's really hard to sell performance in databases when things are only 2 to 4x faster. You really need to be 10 to 50 times faster for it to matter to a larger audience. But with Presto being an interactive system, anybody can appreciate faster wall times because your time is valuable. Next thing I want to cover is remote user-defined functions. Existing user-defined functions in Presto are loaded at deployment time, requiring a restart to make changes. This is not strictly a remote user-defined function server-related issue, but it is being improved upon at the same time with function namespace managers as part of the user-defined function server effort. User-defined functions run in process in Presto with limited isolation, like every aspect of a query, and that makes complex and CPU or memory-intensive UDFs a problem. Blocking user-defined functions are completely impractical because it blocks the thread pools that run queries, starving other queries and making CPUs go idle. We don't want to have to police user-defined function quality. We want properly isolated, fairly scheduled, resource quota limited user-defined functions. User-defined function servers solve this problem by executing UDFs on a dedicated pool of workers. Pages of data requiring remote UDF execution are sent to the UDF server, amortizing the communication cost across multiple rows. Our initial implementation is only targeting projection, which are expressions on columns in the select list. This is sufficient when combined with subselect or CTEs to express most queries. Having a remote UDF server is one part of supporting shared UDFs across multiple systems. Spark and Hive, with better resource isolation, already support blocking and unvetted user-defined functions, and now Presto can as well. With a shared user-defined function definition system, we can support the same UDFs no matter where they are invoked from. Additionally, we don't have to be limited to the language the compute engine is written in. Scaling UDF capacity separately is a double-edged sword. It means we can support blocking our memory-intensive UDFs, but it also means we have created an entirely new pool of resources that we have to capacity plan. We also have to ensure fair scheduling, resource limits, and all those good things. So it's not a free lunch, but we think it's worth it. You can read more about remote UDFs in the linked GitHub issue. So the next thing I'd like to introduce is Fireball. Fireball focuses on addressing issues around the reliability and scalability of Presto's coordinator. A normal Presto cluster has one coordinator responsible for parsing and planning queries, and then distributing tasks to be between 200 and 1,000. And outside of Facebook, some people will run larger clusters. It really depends on your workload. To 200 and 1,000 worker nodes, and then monitoring the results of those tasks. The coordinator has to run several queries concurrently, so we can provide better response times, utilization, and support multi-tenancy. The end result is something that can be overloaded by the workload depending on query shape or bugs. Full GCs on the coordinator can cause timeouts that fail at currently running queries. Fail all currently running queries. When you combine that with retries managed outside of Presto or toxic workloads that may create many problematic queries, then there's a fairly large blast radius associated with the coordinator. Ideally, we could have as many of coordinators as we want and not be forced to heavily utilize them. Because a single coordinator has capacity limits, if you need more than 1,000 workers, you now need to deploy and manage multiple clusters and load balance across them. It's not an ideal scenario. Fireball splits the role of the existing coordinator so that query-specific tasks end up in one pool of workers, and tracking cluster membership and available resources goes to another pool of workers. Resource management is generally going to be a lighter weight process with consistent capacity requirements, but query coordination capacity requirements vary quite a bit. When cluster size is no longer blocked on coordinator capacity, you could have a single cluster per region. You could, in theory, have a coordinator per query if you could orchestrate the capacity. Coordinators are now a resource that can be managed and scheduled. Having a single cluster per region also means that queries can be scheduled across a much larger pool of workers, and that means we can do a better job of finding underutilized workers. This eliminates a single point of failure for clusters, as the cluster can continue to serve queries even if one of the coordinators is unavailable. It's still a single point of failure for the queries executing at any specific coordinator, but it's a material improvement. This also helps with supporting low CPU or low memory coordinators, as you can add as many as needed to achieve the required capacity. You can learn more about Fireball from Swapnil Taylor's recent PrestoCon presentation. So one bonus thing, I want to talk about verification. Facebook is heavily involved in the release and verification of Presto, and there's some unique things we bring to the table there. So we use Facebook's production workload to validate Presto by comparing the results of queries on a new version of Presto against an older version. If you don't have a production workload to use for this, you're kind of out of luck, and it's not very common for the validation and release of a compute engine to be performed by the consumer of the compute engine who would have this kind of workload. So we run this nightly, and as part of verifying the final release artifacts. The errors that are surfaced require manual verification, and there's automation to try and separate high signal errors from low signal ones and filter out false positives due to non-determinism, different result orders, and other issues. This process is scalable enough that we can evaluate tens of thousands of unique queries per release. Workload sampling and comparing results is not a complete testing solution, but it is one form of additional testing. I'd say it's most similar to fuzz testing, since what you find in an actual workload is pretty random, but definitely not as random in some of the ways fuzz testing can be. We happen to find things that only occur in a real deployment, like different metadata and data generated by old versions or other libraries, or that one query in the workload that triggers a bug in the planner that turns out to be 5 years old, but you never found it because it's literally one query in the entire workload that exposes it. All right, thank you for coming. I hope this was enlightening. If you want to find me, I'm available on Presto's Slack channel. Hope you enjoyed it.